Here's a table of standard molar enthalpy values, all right? And they're just numbers. They should be all positive numbers. Every table has variance, so sometimes if you look at something up on Google, it'll be different than the one we use. At the end of problem set 5, I'm pretty sure, or online, I have a table of thermodynamic values. It includes enthalpy, which we used in Chem 221, but it does also include entropy, which we're going to use here. So you can look these numbers up and start using them. But anyway, entropy values always positive. Remember, only 0 Kelvin is that perfect crystal at 0 Kelvin, which never happens, so you can't have 0 entropy. There's some low entropy values. Notice that diamond is lower than graphite because diamond is more compact and hard to break up, but they should all be positive numbers. Let's talk a little bit more about some of the things from Chem 221 and Chem 222 that will help us in the next section, all right? And the first thing I want to do is talk about when you had an enthalpy change or a heat change Q, when you had a energy change for a temperature change, but no change in phase. If you remember from Chem 221, one of the equations we looked at was Q equals mc delta T. And remember that Q at constant pressure is delta H. So if you want to think about it as delta H, that's fine. But anyway, mc delta T is when you have a temperature change, but no change in phase. And change in phase means you have just a solid, or just a liquid, or just a gas. But you're not turning liquids to gas or anything like that. In Chem 221, we talked a lot about 4.184. That's the heat capacity of liquid water. That would be a cool number we'll use a little bit here. But anyway, if you have a temperature change but no change in phase, use Q equals mc delta T or delta H equals mc delta T. Now, if you do change the phase, if you turn your liquid into a gas, or you take your solid and you turn it into a gas, which is possible, then you have mass times heat of something. And that's what I called it. And it's very embarrassing. But the problem with phase changes is that the units are all over the place. The heat of something will have a name like the heat of fusion, heat of vaporization, all these kind of things. And heats of vaporization, heats of fusion, et cetera, they come in different units. So 333 joules per gram, that's the heat of fusion, and 40.7 kilojoules per mole is the heat of vaporization. Those are things for water, by the way. But notice that one is joules per gram and the other one is kilojoules per mole. So when you're doing an enthalpy calculation, the mass in quotes has to take into account whatever the heat value is given. So if you were using 333 joules per gram, your mass would be grams. On the other hand, you're using 40.7 kilojoules per mole, then your mass would have to be in moles in order to get them canceled out. If you have a phase change, there is no change in temperature, but if you change the temperature, you're not changing the phase. And again, this is something we did in Chem 221 back in Chapter 5. We also did this in Chem 222 when we talked about the transitions between solids and liquids and gases, phase diagrams, stuff like that. So if this is looking a little unclear, absolutely go back and review. This was a diagram we used in Chem 222, I believe. It shows the transition of taking ice at minus 50 degrees on the y-axis here, and you're turning it essentially into steam. You could go up to 200 degrees or whatever you want. So notice here there's like some parts with a slope. So like this part right here, that's taking the ice from negative 50 to 0, and that would be some type of mc delta T transition. On the other hand, then there's this kind of flat part right here. And you can see on the y-axis, or excuse me, the x-axis, it's a heat and energy axis. If you're melting something, that's a phase change. You're turning the solid, in this case, into a liquid. It's going to take so much energy, but there's no change in temperature, i.e. the y-axis is constant. Then you can take your liquid at 0 degrees and you can heat it to a liquid at 100 degrees. That part right there, that would be an mc delta T transition. You're not changing the liquid water into solid water or gas or anything like that, but you you are heating it up. Then there's another flat part right here, and this is when you're turning the phase of liquid into a phase of gas. That's a delta H times M, or a heat of something times mass of something. And then once it is a gas, you would have another MC delta T right here for steam as you heated it from, say, 100 degrees to 200 degrees. Anytime you go from a lower temperature to a higher temperature, it takes energy. It's endothermic. On the other hand, if you go from a higher temperature to a lower temperature, it's exothermic. You're going to get that energy out. So these are the kind of things we talked about in past classes, and they will help you out in the material coming up here soon. MC delta T was what scientists use for figuring out the enthalpy of a transition where there's no change in phase, but you are changing the temperature. Well, for entropy, the corresponding equation is delta S equals NC times the natural log T2 over T1. Oh boy. N is often the symbol for moles, and that's what it is here. So in this version of the entropy equation, you want to turn your mass into moles. C is what they call the molar heat capacity. So it would be so many joules per mole Kelvin, all right? And then T2 and T1 are Kelvin temperatures, like always. Now again, this is equivalent in enthalpy. In enthalpy, delta H, or Q, was MC delta T. This is the equivalent expression for entropy. So if you had a temperature change and you needed to figure out the entropy of it, you'd use NC natural log T2 over T1. Here's just an example. If you want to go through this on your own, you can, or you can just take my word for it. Either way is fine. Let's say you had 0.499 moles of water and you heated it from 281 to 294 Kelvin, and you wanted to find the entropy change for it. Okay, well, 0.499 is the moles. T2 would be 294, the final temperature. T1 would be 281. And we do need the molar heat capacity. So the 4.184 number we talked about in Chem 221 is joules per gram Kelvin. We need to turn our joules per gram Kelvin into moles, and it's not too hard. Grams and Kelvin are in the bottom and joules are in the top. So in order to turn it from a grams heat capacity to molar heat capacity, we essentially have to multiply by the molar mass. So 75.40 is the molar heat capacity of water. And we've never used it because we don't usually do molar heat capacities, at least in the earlier classes. But for this problem, that's what you need. So once you have that number, take the moles, multiply it by the molar heat capacity of water, natural log 294 divided by 281, entropy change 1.70 joules per Kelvin. Now, I want to talk here really fast about the difference between a delta S, which is what we're calculating, and an individual entropy S. A delta S is a change in entropy, all right? And a delta S that's positive means you have an increase in entropy. However, there's nothing that says you can't take the water at 294 Kelvin and turn it into water at 281 Kelvin. And if you did that, you'd end up reversing your T2 and T1, and your delta S would come out to be a negative number. A change in entropy can be positive or negative. In this case, you're increasing the temperature, and as increases in temperature occur, the entropy goes up as well. So the entropy is definitely increasing. But if you lowered the temperature, you would be decreasing the entropy, and you'd have a negative delta S. So delta S can be positive or negative. It's a change in entropy. The individual entropies of molecules will always be positive numbers. They are the values that have to be greater than 0. Only 0 is the perfect crystal at 0 Kelvin, which is basically make-believe. A change in entropy, though, can be positive or negative, and we'll start talking about how to interpret that. If you have a phase change and you want to calculate the entropy for it, entropy phase change values, delta S, equals Q over T. Q is the heat transferred in a phase change, and T is the Kelvin temperature. Now, delta H and Q, remember, are related. If your Q is transferred at constant pressure, then that's what equals delta H. So for this particular example, Q is 40,700 joules per mole. And this is, believe it or not, something we did in Chem 221. But just for right now, take it as a leap of faith.
When liquid water converts to the vapor state, its molecules disperse over a greater region of space. This represents an increase in entropy.
So when you calculate the entropy change for this phase change, you would take the Q, you would divide it by the temperature it happens, and figure that out. Now for this particular phase change, this is boiling of water, all right? And boiling of water happens at 373 Kelvin, 100 degrees Celsius, all right? So that's the temperature we're going to use. The 40.7 number, that's the heat of vaporization, and that's something we talked about in Chem 221. But if you look up that number, the heat of vaporization for liquid water going to gas, it's 40.7 kilojoules or 40,700 joules per mole Kelvin. So take that number, divide by the Kelvin temperature, and you're good to go. Now, a phase change in entropy would be equivalent to the delta H expression for a phase change. And again, like we talked about earlier, that's the mass of something times the heat of something. So heat of vaporization would be the 40.7 joules per mole value. You'd multiply that by the mass in order to find the enthalpy. The enthalpy change would be the mass times the heat of that. This is the equivalent. So if you wanted to find the entropy change for a phase change, use Q over T. Let's calculate the change in entropy for the vaporization of xenon at its boiling point of minus 107 degrees Celsius, which is 166 Kelvin. Remember, to go from Celsius to Kelvin, you add 273.15. And it's given the fact that delta H vaporization, the heat of vaporization, hint, hint, 12.6 kilojoules per mole. Okay, so to figure out the entropy change for a vaporization, for a phase change, i.e. going from liquid to gaseous xenon, delta S equals Q over T. And like we saw in the last example there with water, the Q part is related to the delta H of whatever transition you're going through. So we want to vaporize liquid xenon to a gas phase. Q is going to be this delta H vap. Now, the answers there are all in joules. So let's take 12.6 kilojoules per mole and multiply it by 1,000 to get joules per mole, and we'll divide that then by the Kelvin temperature, which is that 166 number. Anyway, you do all this, which is really exciting, I'm sure. 75.9 joules per mole Kelvin is the entropy change for the vaporization, for turning liquid xenon into gaseous xenon. This would be equivalent, once again, for finding the delta H for a phase change here. In that case, we would take the mass of xenon and multiply it by the heat of vaporization for xenon. You can do elaborate phase diagrams for entropy, just like you could do for enthalpy. And earlier we saw the version with enthalpy. In this version, we have entropy on the y-axis and temperature on the x-axis. And you can see how there's different parts. If you're just heating a liquid, that's when you use that NC, natural log T2 over T1 thing. That would be for heating the liquid, heating the vapor, and down here you'd have heating the solid. If you have a phase change, which is melting and evaporation on this particular one, that's when you'd use the heat divided by the temperature part, and you can see how there's quite a bit of entropy involved upon going from, say, a liquid to a gas. Gases have more entropy than liquids. There's also, though, an entropy change going from a solid to a liquid. Liquids have more entropy than solids. So there's all kinds of fun things you can do with entropy, just like we did with enthalpy. Oh, joy.